Hey there, welcome to another edition of Kung Fu Physics. Right now I want to do the second half of a problem that's a two-part problem. A lot of times they pair problems together and they have them share a diagram or a problem description or whatever. It's pretty good for you taking the physics GRE because it kind of saves you some time. You only have to read one problem description and can potentially score 2 points off of the answers. Definitely in this easy mechanics problem. So we're going to do number 5 off of the 1992 exam. Number 5 off the 92 exam. It looks like this. And we already did number 4 in an earlier video. Number 5, the answers, you notice, are more integers and or fractions. And then we have to read the problem to get started. I'm going to reread this again. We did this for problem 4, but the magnitude of the Earth's gravitational force on a point mass is F of r, where r is the distance from the Earth's center to the point mass, assuming the Earth is a homogeneous sphere of radius r. Number 5, suppose there is a very small shaft on the Earth such that the point mass can be placed at a radius of r over 2. What is F of r divided by F of r over 2? So, in a nutshell, it is asking you if you could somehow go down into planet Earth and be halfway towards the radius, what would the force of gravity be like down there compared to the gravity up on its surface? It's an interesting mechanics problem. It's very easy. Incidentally, I have to comment, the first thing that really bugged me about this problem, because I dabble, I know just a little bit about geology as well. And this just makes me cringe when they say that assume the Earth is a homogeneous sphere, because it's so not. Yeah, its density is quite a bit denser as you go down. It's quite a bit denser. Its density is quite a bit higher as you go down. So, but who cares? They tell us the Earth is a homogeneous sphere. We're going to take it as a homogeneous sphere. So what do you get for the force? You can solve this problem very easily, just knowing Newton's law of gravity and some common sense, honestly. The force of gravity is just G times the mass of what's causing the gravity divided times the mass of U times r squared. This is old elementary school stuff, right? Almost. So what is the mass of Earth? The mass is going to be the density of Earth, and they're telling us that's what's homogeneous, right? Times the volume, and so we could just do 4/3 r cubed, right? Okay, this is how I solve the problem. It's, you could, if you knew enough, you wouldn't even have to do this legwork. I mean, you could potentially answer an easy problem like this just by looking at it, just so you know. But this is how I did it. Here's the mass. Now I knew that so the force of r, as they're calling it, is just at the surface, and so that's just G times rho 4/3 r cubed m divided by r squared. And so you notice you get some canceling there, and then the force that's halfway created by that. Now you should recall that the force of gravity, as you descend into a uniformly distributed mass, it's sort of weird, but when you're inside, you can treat whatever is beneath your feet as a point mass and calculate the force that way. Everything around you, in the shells around you, cancels out perfectly. I always thought that was a really cool thing, because it seems weird that it doesn't matter where you're located. If you're located in a sphere of any thickness, of any kind, the gravitational force caused by that sphere cancels out. It makes sense if you were right at the center, that would be symmetrical, but it seems really interesting that if you were on the outer edge, but since you're closer to that outer edge, there's less of that there, and then there's more of the rest of the circle out over on the other side, and even though you're further away from it, it all cancels out. I just remember learning that in freshman physics and thinking it was cool. If you don't realize that, in other words, so here you are halfway, this is 1/2 the radius here, and you're calculating the force at that point. All this stuff, that's the other half, this shell does not affect you. There's no net force caused by that shell on the outside. Just want to make that clear because that would potentially be a stumbling block in this problem. So you just calculate what's left on the inside as the mass and go from there. So rather than R, we're taking 1/2 R. We're cubing that. Oh, and then down here we've got 1/2 R squared, right? So, all this junk, and this is the ratio that they want, and you can see it is going to cancel out. All of this cancels out. What you're getting, now here you have to be a little careful. Here I just kind of callously cross that out. And of course that's going to happen here, but you're going to get these cubes here. So this is going to be R divided by 1/8 R squared divided by 1/4 R squared, and that's going to cancel. So you get 1/8 divided by 1/4, or 1/4 over 1/8. Or 8 divided by 4. It's just how I'm running the math through my head. However you run the math through your head is just fine, as long as you do it right, of course. But so that's going to get 2. So in other words, the force halfway down is half as much. It's linear. It's linear. Whereas in the other case, the force goes as the square. In this case, it's linear. In other words, if you go halfway down the Earth, if the Earth was a uniform density, if you go halfway down in that, the force acting on you goes down by half. It's 1-to-1. It's linear like that. I remember learning that as well from freshman physics. I'm just thinking that was just really interesting. So, so yeah. It's got an answer there that we can run with. Answer C says 2, and that's the one I'm going with. So that's all for now. Thanks for watching as always. See ya.